One of the most commonly used data analysis techniques in engineering and many other fields is linear regression. With linear regression, we are able to collect data and form relationships between the independent and dependent variables of that data. Linear regression is a commonly used technique used in many fields, like in the environmental world, medical world, or even within a factory setting. Linear regression, as I mentioned earlier, provides a predictable way to quantify the relationships between two variables, even when significant uncertainty and measurement error exists. So what we're basically going to do with linear regression, we'll have raw data that we've collected, and we will try and find a mathematical relationship to represent that data. We will use this heart rate after exercise data that I've already collected. This data shows the heart rate of an individual after doing jumping jacks for a certain amount of time. Before we perform linear regression analysis on this data, we must first plot the information. We went over plotting in a previous video, so let's exercise those skills here. In order to plot this data, I'm going to insert a scatter plot. Remember, we don't know the relationship between the data points, and therefore we need to do a scatter plot, not a line graph. When I insert my scatter plot, it opens up this blank chart area. I'm going to click Select Data, and I'm going to add a data series. When there's only one data series, the series name will be the same as our chart title. Here, I'm going to put heart rate versus time. You should immediately know when I say heart rate versus time, what's on my x-axis and what is on my y-axis. Remember, we always title our charts y versus x, dependent variable versus independent variable. So here my series name is heart rate versus time. My x values, I'll click into that section of the dialog box and highlight my x values, which are my time values. And then I will click into the series y value section of the dialog box, erase what was previously written in there, and highlight the y values of my heart rate. Now my data is on my chart. I'll click OK. There's no extra data that I'd like to plot, so I'll click OK again, and I see that my data has been placed on the chart. There are a few format things that I'd like to change. The big thing that stands out is that I don't have my x-axis and my y-axis labels. So I'm going to click the plus sign and check axes titles, and then I'll click in and I can change the name of each title. My x-axis is time in seconds. My y-axis is heart rate in beats per minute. Now I have my information graphed on a scatter plot. From here, I can make some assumptions about maybe what is the heart rate at 5 seconds or 15 seconds or 25 seconds. And maybe I can make some predictions about what it would be at 45 seconds or 50 seconds. However, if I can represent that data mathematically, I can more conclusively say what the value of heart rate is for 5, 15, 25, or predict the value for 45 or 50 seconds. We'll use linear regression in order to create that mathematical model. Previously, probably in your high school or junior high years, you may have done a similar process to this when you found a line of best fit. When you found a line of best fit, you probably just eyeballed how you would draw the line that represents the data, that best fits the data. You probably eyeballed it and just drew a straight line as best you could. The problem with this is dependent on who's drawing the line will dictate the shape that the line takes. You can see that student 1 might have drawn the red line that I have on the screen, and student 2 might have drawn the orange line. The orange line and the red line have vastly different slopes. The orange line has a much steeper slope than the red line, and they also have different y-intercept values. So the equation of these lines are going to be different. When we use linear regression analysis, we're able to take that error away and get the same value for slope and y-intercept Let's look at this in more detail here where I've drawn our scatter plot. Remember, if you were doing the line of best fit, for instance, if you had to find that equation of the line, depending on how you draw that line, you would get a different equation of the line. Let's investigate the equation of the line so that we can reference those terms later on when we get more detail into the linear regression analysis. This is my line of best fit. And with this line, I can make an equation of the line. You should recall from your classes, the equation of a line is y equals mx plus b. Now, we can find this equation of this particular line using what we know about slope and intercept. On here, in this equation of the line, m represents the slope and b represents the y-intercept. In order to find the slope here, we have slope is equal to rise over run, which is y2 minus y1 over x2 minus x1. We can calculate this slope by picking any 2 points that fall on our line of best fit. So we're not looking at these raw data points that we have marked here. We're looking at the line of best fit because that's what we're trying to find the equation for. Now I can pick any 2 points, and so this is where error might come in when you're doing this line of best fit method without linear regression analysis. So I can pick any 2 points. I'm going to pick this point here, which I see as 0, 70, and I'm going to pick the point here, which I see as 40, 107. Again, this is where error comes into play because you could have picked 2 different points, or you could have even picked the same 2 points but seen them a little differently. You might have said this is 40, 106. So your slope and your intercept are going to be different values from what I get. So for y2 we have 107 minus y1, which is 70, and x2 we have 40 minus 0. So when I calculate that slope, I get 0.925. Okay, now we can calculate b, and b is simply the value of y when x equals 0. So if we look at our y equals mx plus b equation, we're saying the slope is 0.925, our x is 0, and we want to find the value of b. When x is 0, I have that the y value is 70. So b is equal to 70. So my equation of the line is y equals mx plus b, where y equals 0.925 x plus 70. And another thing that you should do when you're writing the equation of a line that's representing specific data, instead of writing it in terms of y and x, you should change those variables to things that make sense. In our graph that we have, what is the value of y? Y is representing heart rate. So instead of y, we should say heart rate equals 0.925, and our value of x is time plus 70. So now this would be my equation of this line that represents my data. So I have my heart rate equals 0.925 times time plus 70. So I can use this equation of my line to find the value of heart rate at this point along the line, or this point, or this point, or even predict it as it goes further out. However, as we mentioned earlier, the problem with this technique is that you could choose 2 different points to represent. You could choose 2 different points to find your slope. You could have a completely different line drawn. And so there's a lot of error that can be introduced when you're finding the equation of the line in this method. So we really need to use a more precise, a more consistent method in order to find our equation of our line to represent that data. So let's look at how that's done. This red circle on the screen represents one of our raw data points. And then we have a line of best fit, the line that does represent the data in the best possible way. And with that data point, we not only have an x value of our raw data that's corresponding to a y value, but that same x value has a new y value. We'll call it y fit because it's the y value that's on our line of best fit. And so we can calculate the value of that y based off of the equation of the line that we're able to find using linear regression. And so when you're looking at this information, you have a y value that's associated with your raw data point, and you have a y value that's associated with your line of best fit for the same x value, as you can see here on this diagram. That space between those y values is what we'll call error. And what we're trying to do is we're trying to minimize that error as much as possible for every single data point along the line. And so linear regression generates the best line by minimizing the squares of the error. And so what it does is it takes that error and squares it, and it allows you to find the optimum values of m and b. This is called least squares linear regression. And that's the process that we're going to use in order to do our analysis. We will apply this to our pumps later on in the quarter when we collect data on how our pumps are performing. Let's jump back to our data that we started with at the beginning of class, our heart rate versus time data. Let's apply the least squares linear regression analysis on this data so that you can see how you would find the slope and the y-intercept to find the equation of the line to best represent that data. We know that the equation of the line is y equals mx plus b. This is our goal. We eventually want to have an equation that represents our heart rate versus time data in the form of y equals mx plus b. In order to get that, we need to find m and we need to find b. I'm going to spare you the derivation for finding the slope and b equations, but let's talk through what they are generally so that you understand what's happening in the equation. In our slope equation, we have this n. N is the number of data points. So here, my n is going to be 1, 2, 3, 4, 5. 5, because I have 5 data points. Then each of these terms has this funky e. That's a sigma, and that represents summation. So each one of these terms, I'm going to find the individual version of them, and then I'm going to add them together. So if I'm looking at the summation of xi times yi, I'm looking at the individual data points of x times y, and then I'm going to find each one for every set of raw data, and then I'm going to sum them together into one term. Same thing here, summation of x, that's going to be all my x values added together, summation of y, all my y values added together, and then again the n shows up, that's the number of data points, the summation of x values squared. So individually I'm going to square each x value, then I'm going to add them together, minus the summation of x's and that value squared. So notice the difference between my two terms in my denominator here. This is going to be summing all my x's and then squaring that value. Similarly on b, you have the sum of y. Now notice you have to use the value you find for m in the equation for b, and then summation of x's divided by the number of data points. The easiest way to do this would be to utilize your Excel document and create your chart so that you can find the different terms that are needed for the m and b equations. And so the first thing that we have n, and n is the number of data points. I mean, it's easy right now to just count that there's 5, but I want to show y'all a new function that you can have in Excel. So I would probably put it somewhere out of the way so that it doesn't get in the way of my calculations. N, and then in order to find that value, say for instance you had a lot of different numbers and it wasn't as easy to count as it is here for, it's easy to count that 5. So I can do equals, there's a formula built into Excel called count. And what the count formula is going to do is exactly that. It's just going to count the numbers. So I'll start with my equal sign. I'll type COUNT, open parentheses, and I'll highlight just the x values. Don't highlight all of them. You're only highlighting the x values. This will count the number of independent data points that you're going to have. Hit enter and notice how it says 5. Now here I can call on that 5 when I start calculating my slope so that it's always consistent. Say I added a data point here. Let's say I inserted and I made 15 and I said it was 81. And notice it added one to my count value. So now it's at 6. So it knew intuitively to add that in there. Now I don't want that data point, so I'm going to erase what I just put. But I just wanted to show you that it's better to use the count function as opposed to physically counting, because if you had to add a value or take away a value, you can have that automatically done for you. Now here I'm going to add a column called x times y, because that's my term here. I need to multiply x's times y. I have a column for my x values. These are my x values. These are my y values. I like to put labels on here to help me remember what everything is. And then I also need an x's squared. So I'm going to add x's squared here. Now I can do the little caret 2, or I can put a 2, highlight the 2, go to my font. Notice how there's a little arrow at the bottom of the little font box. Click on that and make it a superscript. Now I have my x's times y's, I have my x's, my y's, my x squared, and I have my x's that I can square. I kind of also want to do just a few formatting things, make these centered just so it's nicer to look at, maybe make them bold. And now let's start doing the individual portions of this. Now I haven't started doing the summations yet, and that's because I'm going to do those at the end. So I need to do first my x's times y, so I'll do equals my individual x times my individual y. Now you think about this for a second. Do I want to make anything an absolute reference, or do I want everything to be relative references? If I want to multiply each individual x times each individual y, then I don't want any absolute referencing. I want this to be completely relative referencing. So I hit enter. It's 0 times 68, that makes sense. And then I'll drag this down. I'll click in and make sure it's multiplying the right things. So check it. It's doing A9 times B9, which is my x times my y, and that's exactly what I want. And now let's do the x's squared. So I'll do equals. I'll click my first x cell, and then I'll do the caret, which is shift 6 squared. Hit enter. 0 squared is 0, so that makes sense. I'll drag it down, and then I can click on 10 squared, which is A6 squared, and that's correct. 30 squared, which is A8 squared. And so I'm feeling confident that my x's times y's are right and my x squareds are correct. So I'm looking back at my slope formula. I have my n, I have my x's times y, I have my x's, my y's, my x's squared, and my x's here. The only thing I need is my summation. At this point, what I would like to do, just to make this a little bit clearer for me to follow, I like to insert a column on the left side of all my data, and I like to call it summation. That way I don't get it confused with my raw data. And another thing that I do when I do this is I like to highlight these a certain color so that I, again, don't get them confused with my raw data, because it does make a difference. It's also good to take a second and just keep formatting things to look good. I'm going to make these all centered. I'm going to have borders around it. And so in order to do the summation, again, it's just a built-in function. You do equals sum, open parentheses, and then highlight what you want it to sum. Close your parentheses. So I wanted it to sum B5 to B9, and it has B5 to B9. Now remember, you can drag a formula horizontally, and if I do that, it should populate my summations accordingly. So it has C5 to C9, that's correct, D5 to D9, and then E5 to E9. So now I have my summations. These 4 terms here, along with this 5, are the only terms that I'm going to use when I'm calculating my M. You never highlight any of these when you're actually doing the calculation for M. I've seen students make that mistake too often. We're only using these summation terms. So the summation of x times y is this term here. It's not multiple numbers, it's just one singular number. So I'm going to put a label here for M, and I'm going to start my equation. Notice how my numerator and my denominator both have 2 separate terms that are subtracted. And so what I want to do is I want to keep everything in my numerator. So I'm going to start with an open parentheses, and I'm going to put everything in my numerator in that parentheses. I'm starting with equals, open parentheses. I have n, so I'm going to click on the cell that has my n value, which is I3 for me. Then I'm going to multiply it by the summation of x times y. Remember, that is just one term. So I'm going to click over at that one term, which is my summation of my x times y, which is D10 for me, minus the summation of my x's, so I'm going to click that cell, B10, times the summation of my y's, which is my cell C10. That completes my numerator. So I'm going to close the numerator with parentheses, and then I'll do divided by, open parentheses, because I want everything in my denominator to stay in my denominator, and it's n, which is I3 for me, times the summation of my x squared values, which is E10 for me. Notice it's my summation of my x squared values. I'm only picking that one number, not all of these numbers. It's just the one. Minus, and then I have the summation of my x's squared. So I'm going to click on my summation of x's, then I'm going to do the caret to do a square, and then I'm going to put a 2, so it squares just that term. Close my parentheses because that's the end of my denominator, and I'm going to hit enter. I get 1.15 for my slope. Everyone should get the same slope value. That is the point of using least squares linear regression. If you did this with me and you did not get 1.15, then you should go back and check your equation. I'll click into it so you can press pause and check it. You need to go back and see where you made the error. The beauty of least squares linear regression is that everyone should get the same mathematical model to represent their data. Now let's calculate B. B is equal to, and let's put our numerator all in the numerator with parentheses, the summation of y, which we already have in our table, minus m, so you can click on your m value that you just calculated, times the summation of x. That concludes our numerator, so I'm going to close it off with parentheses, divided by the number of data points, which is our value of n. Hit enter, and I get 67.2. So everybody should get that same y-intercept value. So I can say, I can go here and I can insert an equation. So on your ribbon interface, if you go to insert and you insert equation, you can type your equation that you just calculated to be heart rate. Remember, you should call it what it's actually referencing, not y and m and x, but our y values are heart rate. So it's going to be heart rate equals m, which is 1.15, times x. In this case, our x values are time, plus b, which is 67.2. And so this is my equation of my line. So this is my goal. This is the equation that I wanted to reach. So I'm going to put it above my chart so that you can see it a little bit more clearly. And I'm going to do just a few more formatting things to kind of set the n and the m and the b apart because I just calculated those. And so that's least squares linear regression analysis. Now the last thing that you should do to complete the analysis is to show that line of best fit on the graph that you created previously. And so how can we represent that line? Well, we have the equation of the line, so we can find the specific y value points that go along with the x values that we have collected, 0, 10, 20, 30, and 40. We can use the equation of the line to plug those x values in. We can plot those points, and now that we know the relationship between those, instead of plotting them as individual points, we can plot them as a line. Let's do that here. I'm going to title this column heart rate from line of best fit. And I'm going to use my x values along with my equation that I just found in order to find the y values that are associated with the x values for my line of best fit. My heart rate for a time of 0 equals slope times the time plus y-intercept. And that makes sense. It's 67.2. My time is 0, so my y-intercept is 67.2. So it should be that value. If I drag it down, remember, don't include the summation values. We're only using our raw data. I get zeros for some of my terms, and I'm feeling like that's probably an error. If I click in, I can see that my slope and my y-intercept move down relative to the formula, and I know that I need to do some absolute referencing here in order to get the values that I actually need to calculate. So I'm going to go back into my formula. I want my slope and my b to always stay the same. So I'm going to put dollar signs around the column and the row. A quick key in order to get dollar signs around those terms is just clicking into that term within your formula and pressing F4. It automatically puts dollar signs before the column and before the row. I need to put absolute referencing along M, and I need to put absolute referencing for B. When I hit enter and then drag that formula down, remember not including your summation values, I now get the terms that I was expecting. Now I can go back in, click on chart design, click select data. I'm going to add a new term here. This series is going to be the line of best fit. I'll title it that. My X values are again just the same X values as I've used before, but my Y values are now the Y values that I calculated using my line of best fit. I'm going to click OK, and I can see that those values have populated on my graph. I'm going to click the heart rate versus time. Remember, we named it heart rate versus time because it was the only series that we were graphing. And I'm going to edit it, and I'm going to call this raw data now, because that's the raw data that I collected in order to plot these data points. I'm going to click OK, and I'm going to format my chart. Now, right now, I have two sets of data points, my orange data points and my blue data points. I don't know which one are which, so I need to show my legend. Now I know my blue data points are my raw data points and my orange data points are my line of best fit data points. I also need to show a chart title because when I added the second series, it took the chart title off. So I need to go back here, and remember our chart title is always Y versus X, dependent versus independent. So it's going to be heart rate versus time. Now for my line of best fit, if I'm calling it a line, I need it to be a line. Right now I just have data points. And what we just did when we found this line of best fit was we found a line that represents our raw data points, which are our blue points on the graph. So these orange points here, I don't want them to be points, I want them to be a line. So I can click on the individual data points. So notice how all my orange dots are now highlighted. Right click and format data series. It opens up a dialog box. Then I can adjust the markers for that data series. And so if you click on the paint can, there's an option for line and there's an option for marker. The marker is the individual circle. The line is what's going to connect them. I want to put a solid line. You can change the color. You can make it look however you want. And then I'm going to click over here on marker, and then you have some options for marker options, fill, and border. We're going to go to marker options, and I'm going to click none. That removes the data points that were associated with the line of best fit because we don't really want those data points. We just want that line so that it represents the line of best fit that mathematically represents the data. And now we have a line of best fit that showcases the relationship between the variables within our raw data. To conclude, I want you to see the power of using least squares linear regression so we can represent data using an equation, and we can have a consistent equation between people so that everyone has the same line of best fit that represents the data, and it is the best fit that represents that data.